thank you for the introduction, and thanks for having me back. Real pleasure to be here again. Yeah, so my name is Frederik. I'm a PhD student at the Technical University of Denmark, and we have been doing a collaboration with Haldor Topsøe, which is a company in Denmark, on numerical modeling of CFB riser for cracking of sugar into glycolaldehyde. Also other things, but mostly glycolaldehyde. So the presentation I have brought with me today will focus on this. And we're looking at a circulating fluidized bed in pilot scale. And we've been working for the past couple of years on getting the hydrodynamics right. So this talk will be mostly about some of the additional features of the flow. So we have a sugar solution that we're injecting into the riser. So naturally we need to handle that gas liquid jet in some way. So I'll be talking a bit about how we're actually doing that using CPFD Barracuda. And then we have a sugar cracking kinetics that we also need to account for in order to predict the yield of glycolaldehyde. But maybe just to set the stage a bit. So sugar cracking into glycolaldehyde is a relatively new technology that has been underway for 5 or 10 years or something like that. And the whole goal is basically to supersede some of the more traditional fossil-based ways of producing chemical compounds that we use, for example, in the production of plastics. So glycolaldehyde can be converted into ethylene glycol, which is used in production of PET bottles, for example. So if we could find a proper way of doing this sugar cracking at a low cost and a high energy efficiency, then that would actually be a quite good way in terms of supporting a green transition. So my part of the project is basically to see if I can figure out if we can basically develop a CFD model for supporting scale up of the technology. So there's been a lot of work going on in bubbling fluidized beds, trying to figure out how does this sugar cracking actually works, because it's not something that we know a lot about. So there's been Kinetics developed based on bubbling fluidized beds there, and we're trying to make it work on sort of a larger scale in circulating fluidized beds and using numerical tools to help scale up the technology. The system that we're looking at is actually the same system that I presented 3 years ago. So there we were presenting some results for cold flow simulation of this dual circulating fluidized bed that consists of a reactor loop and then a regenerated loop. Today I'll be focusing only on the riser itself. So this is consisting here of a feed conditioning zone where we have solids coming in at a rather high temperature. And then these solids basically are intact with a feed that is basically a gas liquid feed, where you have droplets or liquid consisting of glucose and water that then evaporates, cracks. And then upon vapor expansion, you go from this dense feed conditioning zone into a fast fluidized bed, relatively dilute fast fluidized bed, where we're then measuring temperature, pressure in this pilot scale circulating fluidized bed. And then we have an outlet where we can separate gases from solids. So a lot of the sort of the complexity to the flow arises from the feed conditioning zone where we have this injection of liquid. And I've taken a little bit of more or less just stealing this schematic here from one of the CPFD presentations, where you actually see sort of you have the solids, you have a nozzle that basically injects our droplets at a specific velocity with a specific size distribution, and they can then, within Barracuda, contact with the solids. I think James will probably talk more about this later today, I think. And the droplets are basically modeled in the same way as the solids. The only difference being more or less that the droplets are allowed to evaporate. That's one thing. And also they can distribute their liquid onto the solid, so you get a thin liquid film from where you can then also evaporate the liquid or crack it. So naturally we would like to optimize this behavior down here so we get the liquid spread to as many particles as possible to get the fastest evaporation and the largest surface area. So in order for this to model, or this to work basically, we need boundary conditions and input conditions for this feed conditioning, or this nozzle here. So we've previously developed methods for how to predict what the injection velocity is going to be based on a momentum balance, and that seems to work quite well. Then naturally we also need basically material properties for the liquid itself, and that depends on, of course, temperature, but also on the concentration of glucose that we have in our aqueous solution. So we also have basically models for that to predict what are our material properties, viscosity, heat capacity going to be. And then the last thing is that we need to specify a droplet size distribution. There's actually been a lot of work going on in terms of discussing whether at all there is atomization going on when you're injecting liquid into a dense fluidized bed. But in this case, we're working with a sort of a Lagrangian approach. So therefore, we need, within the framework of Barracuda, to specify what is the droplet size going to be. Even though it might not be completely realistic, we need to specify it. So we've been doing a lot of work in trying to figure out the best way of doing this, such that it's the most consistent in the way that we're working. I'm not sure why these look like this though, but it's fine. So what we did was we took the spray nozzle, which is a 2-fluid spray nozzle, and then we basically took that out of the reactor and put it into ambient conditions. Set up an optic measuring system to basically measure what is the droplet sizes at different operating conditions of our nozzle. And the results are shown here, as you can clearly see. And basically what we did was we varied atomization gas, feed flow rate, and also the glucose concentration, did measurements of the droplet sizes, and then used a Simmons equation that we found in literature to basically predict what is the, to see if we can get a proper fit. And as you can see, there are some dots here, and then you get the lines. Basically, we're actually able to sort of predict what is the droplet size going to be on an overall basis quite well for the ambient conditions. And because this Simmons equation basically contains properties that are dependent on pressure, temperature, we can then extrapolate into the operating conditions of interest. So we now have a quite good way of sort of predicting what is the sort of mean diameter going to be at the operating conditions that we're looking at. Then what we also found from the experiments was actually that normally what we then do would just apply a Rosen-Rambler model or something like that to get the size distribution around this mean. But we actually found that only for when you have a large amount of gas going into our 2-fluid nozzle compared to the amount of liquid we have, that is only the case, well, then you get a Rosen-Rambler distribution. But if you start decreasing your atomization gas flow rate or increasing your feed flow rate, then you go to something that, nice, perfect. It's like getting glasses for the first time. Then you actually go to a lot more of a poor atomization. So you get this linear distribution here for a lower gas-to-liquid ratios. And often you're not operating at very high gas-to-liquid ratios. You try to reduce that to as much as possible, 1 weight percent, 2 weight percent, something like that. So what we did was actually we took the Rosen-Rambler model, which is this term here, and then modified it slightly so that it depended on the gas-to-liquid ratio and that it had sort of this linear term. So this is the dotted lines are the normal Rosen-Rambler model, and then the modified one is here. So basically, as we go to high gas-to-liquid ratios, they more or less converge towards the same profile. But for lower gas-to-liquid ratios, we see a lot better fit. So again, we use this in combination with the Simmons equation to then predict what is our droplet size distribution going to look like for the operating conditions. Here it's 60 weight percent glucose and a gas-to-liquid ratio of 50 weight percent. And it actually makes quite a bit of difference in terms of when you're comparing different operating conditions, what is your droplet size in terms of how well the liquid is distributed onto the solids in the software. So it is actually a big point here. So we could now, having the hydrodynamic part of the model set up, we could then focus more on the kinetics model. So one of my previous colleagues did a homogeneous gas phase kinetics model back in 2021, which is basically, this is a schematic showing some of the reactions that basically allows us to, in the gas phase, crack glucose so it can react through an isomerization reaction to fructose, or you can also have a retroaldo reaction to, for example, erythrose that then again reacts and produces glycolaldehyde. That glycolaldehyde could then further decompose under high temperatures to mostly it's just CO and CO2, but we just call it a lump C species. And these reactions are governed by Homogeneous rates that are also, one of them is a bimolecular one, so it depends on the water content in the system. So we took this model basically as it was. It's also published, so you can find this in literature, and we implemented it into Barracuda, which is quite straightforward using that framework. And then the big challenge comes in the fact that we have liquid droplets being injected into the system, but everything we have in terms of kinetics, that's on gas phase. So we need to transfer that somehow. It actually looks like how we do it in FCC, but in this case we don't have this assumption of instantaneous evaporation. So we know all about our droplet sizes, we know our inputs, we know our size distributions, velocities, everything like that. They're being distributed, evaporate, collision model, whatever, all that stuff. So that's fine, that's step one. And then we have the pure evaporation of the water part of our droplets, which is quite straightforward because, well, you have a heat of evaporation. You also have a vapor pressure that is, well, it's slightly dependent on the concentration of glucose in our system, but we can account for that. So that basically just produces steam upon evaporation. But then glucose, that's a bit of more of a hassle because that is not really prone to evaporate. It doesn't have a vapor pressure. So what the heck do we do here? So we just said that we don't require any heat to be extracted from the gas phase in order to sort of evaporate the glucose. But we do say that it has the same vapor pressure as the water, so that it is basically transferred from liquid state to gas state at the same rate as we're evaporating the water. So that produces our gaseous glucose that could then enter into our kinetics model. And then we have, of course, reaction enthalpies here that are dependent on heat capacity at different temperatures, but also more specifically the heat of formations for the different products that we're looking at. So then we can then have the thermal part of the system working as well, and then predicting the yield of glycolaldehyde and some of the other products. So we took all of that and we combined it into one simulation. It's quite heavy with all the reactions in place, and we tend to get quite low time steps also with the injection, high velocity injections that we get in the feed conditioning zone. So we started out simply by simulating the first 40 seconds using no reactions at all, and then use that as sort of initial condition for the further simulations, and then switch on the simulation or the reactions here. We have a constant flow of solids going into the system, so naturally the bed mass inventory is bound to change depending on whatever drag model you have, depending on the operating conditions of your nozzle. But that is actually quite good at finding a steady state level here. We also see quite difference between just having 100% evaporation and having the reactions in place. That actually makes a difference there. So it's not equally endothermic, the two reactions, whether you're considering cracking compared to pure evaporation. So as I said before, we do have measurements of some stuff. We can measure yields, we can measure temperature and pressure across the height of the riser, but it's quite limited, the amount of data that we can get from the setup. Also because it's due to proprietary reasons not able for me to show most of the actual interesting results. But I am allowed to show this here, which basically goes to say that in terms of the hydrodynamics of the system, we're capturing the overall pressure drop, pressure distribution quite well, which is also what we saw from the cold flow simulation. So quite happy that seems to work both on cold flow and hot flow. If we then look at the thermal behavior a bit, then in terms of measurements, we're seeing a slight decrease across the height of the riser due to heat losses and reactions occurring, and then we get an outlet temperature of around 490 degrees Celsius. But the simulations there, we are predicting temperatures around 520 degrees. Here I'm showing plots of the temperature in the center of the riser, and then here at the wall, and then there's this cross-sectional average. So we're quite over predicting the outlet temperature, which is a bit annoying actually. Most of it is due to the fact that we're not accounting for heat losses in the system. That's a bigger discussion. It's quite difficult to actually implement in a proper way considering the experimental setup that we have. Then uncertainties related to, for example, heat of formations for these sugars, which are really difficult to actually find in literature. And then the simulation approach, some of the assumptions in terms of how we are evaporating the glucose. But it's interesting to note from the simulation that we see quite big difference between the temperature near the wall and the temperature in the center of the riser due to a core annular structure. And we don't actually reach the same temperature at the outlet of the riser. So there's a quite slow radial dispersion of thermal energy there, which we're actually not expecting. And also, if you look at the temperature difference between solids going up through the riser and gas going up through the riser, there's a big gap there. So we're not fully utilizing whatever energy we have in our solids. So we're actually now working on approaches to improve this sort of distribution by baffles, for example. So there's an experimental campaign based on these results coming up here in the fall to improve this. That's actually quite nice. If we look at the results from the kinetics model, then this is on a vertical plane through the center of the riser. Here in the bottom part, we have the feed conditioning zone with the injection of glucose that then evaporates and goes quite fast, actually. So we don't have to get way far up into the fast fluidized bed before we actually don't have any glucose left at all. And if you at the same time look at the mass fraction of glycolaldehyde, you see that actually reaches a quite high level relatively quickly, which is quite good for the conditions we're looking at. If you then look at this lumped C species, the CO, CO2 mostly, then it's quite interesting to see actually that on the opposite side of this inlet, we only have one inlet for the solids. We see this high concentration region. It's a bit more easy to look when you look at time average values. There it's quite clearly defined. It's not something that has a lot of effect on the outlet concentrations of glycolaldehyde, for example, but it clearly goes to show that there's some optimizations that can be done in this region to further improve fluidization, get a more uniform distribution, and basically reduce this recirculation or dead zone. So we're actually also working on trying to get that by using, let's say, several inlets down here. I think this is the last slide, so I hope it's okay on time. So here's a plot showing the yields of different product species along the height of the riser, and you clearly see this rapid increase in the yield of glucose during evaporation, but then just as fast a decrease with the cracking. So that goes really fast, and you see most of it is actually gone just after a third of the riser. So the rest of the riser is basically not being used for much of the cracking other than whatever decomposition we get from glycolaldehyde to the lump C species. So that there could be an optimization with respect to the residence time of the system. If we look at the yields and compare them from the CPFD predictions with the kinetics model, the homogeneous kinetics model in place, and compare that to the experimental measurements, one of the interesting things is that we see a 50% overprediction in the glycolaldehyde yield. So we're not really happy with that, to be honest. There are several reasons and for why this is happening. Some of them I'm not able to sort of elaborate on, unfortunately, but it's clear to see that we're including a homogeneous kinetics model that is only indirectly dependent on, let's say, solids distribution, stuff like that, through, for example, temperature or water partial pressure. So definitely we need to do a lot more in order to couple the reactions directly to, let's say, distribution of solids through, could be heterogeneous reactions, heterogeneous decomposition, liquid reactions, which I think is also available in some of the new versions of Barracuda, so really looking forward to testing that out. But there's definitely a lot more to be done there. But it's a bit sad because we have a quite nice setup for all the thermal parts, all the hydrodynamics part of it. We have this liquid injection, dispersion, evaporation model that seems to work quite well. We have been using a lot of time on the sort of the boundary conditions of it to get that right for the feed conditioning zone. And we have seen quite good agreement both on hot conditions and cold flow conditions in terms of overall pressure. Thermal parts still lacking a bit, so we're doing whatever we can to improve that. And then we're actually able to use the CFD model without the kinetics model just to predict some of the recirculation zones and undesirable behaviors in the fast fluidized bed part of the riser. And then the big problem, definitely, the homogeneous gas phase kinetics model that we will be working on expanding. Yeah, so with that, I just probably should thank the people paying my salary. And if you have any questions, please let me know. Thank you.